We're very pleased to have Brian Conrad for our joint with Simon Center, as you can see, Colloquium on the ABC Conjecture.
Okay, thank you very much. I grew up about 20 minutes away from here, and I first learned linear algebra over some other building on campus, so it's always nice to be back. Brings back long-distance memories. So today I'm going to talk about the ABC Conjecture, and some of you may be wondering about the current status of the proof and so on. And anyway, that's a little more complicated situation to explain, so I'll discuss that at the end after the video camera's turned off. So just a little bit of history. So the conjecture, I'll discuss a little bit later where this originally came from and what the statement is and what led to it. But it's largely due to these three gentlemen at the top here, David Masser and Joseph Oesterlé, and they were trying to better understand a conjecture put forth by Sphero, who's the guy on the right. So although the conjecture was formulated in the mid-'80s, it turns out, as we'll see, it's very easy to state in one formulation, but it has many striking consequences, which of course means it's quite difficult to prove. So Shinichi Mochizuki was sort of known to be working on it largely on his own since roughly the late 1990s. And then about a year ago, he announced he'd done it. And he had these 4 huge papers, 1,000 pages, which all relied on many earlier papers, which was also hundreds and hundreds of pages. And so a kind of daunting task to decipher all that. So we'll get to that later. But the main thing I want to convey in the talk is what was this conjecture about, why are people interested in it, and what consequences does it have? Why is it considered such an important thing? And so the first topic I'll discuss is the general area of what's called Diaphanetin equations. So this is a very classical topic within number theory. And we'll look at a variety of examples from our last theorem as one example. And then, having surveyed several different kinds of Diaphanetin equations, we'll discuss a bit about the ABC conjecture, both the formulation as well as how it connects back to some classical Diaphanetin equations, and either to understand things that were in a new way, that were understood in other ways, or else to solve other problems that were largely untouched. And then we'll go into that in a little bit more detail in the last part of the talk. So this is a quote from Dorian Goldfeld, which nicely captures the tantalizing nature of this conjecture. There are many problems in number theory which one doesn't really have a clue how to attack, and in fact there's a whole web page about this. And yet in many situations, if you can understand this very concrete statement about numbers that we'll formulate, it turns out to have very striking consequences for a variety of problems that we don't really know how to attack. So let's first discuss a bit about Diaphanetin equations. So the classical definition would just be it's a polynomial, perhaps in several unknowns, polynomial equation, or it might be a system of equations. And the idea is we want to find integer or whole number or perhaps rational solutions depending upon the particular equation or system of equations. So sometimes it has simple geometric interpretation like a line or a circle. Here are some higher degree examples which correspond to elliptic curves. We might have, as I said, more variables and more equations considered simultaneously. But the two basic questions we're interested in, whether we're studying one equation or several, is the nature of the solutions, be they integers or rational numbers, finitely many, infinitely many. Even when it's infinitely many, maybe there's some finiteness to it somehow. And when there are finitely many solutions, can we find them all? So for example, let's say an equation like this one, which we'll see is known to have, or its variance, has finitely many integer solutions, but sometimes we can prove that without giving a bound. Right? You might want to give a bound on a box which has to contain any possible solutions, and then you could find them by search. But can we give some a priori bound on the size? So this very classical example, this is an instance of what's called Pell's equation. This is a little quadratic guy. And by using continued fractions or other means, this has actually infinitely many solutions. And if you've never seen it before, it might not be apparent, but there's actually a very simple formula that will generate all of these solutions. And more generally, the same thing if you replace 7 by any non-square positive integer. This also has infinitely many integer solutions, and it's been understood since the 18th century how to find them all. On the other hand, if you increase the degree from 2 to 3, so this we can think of as geometrically, as in terms of conic, but when we go to higher degree, things become more complicated in interesting ways. So this one, turns out, has only two solutions. This is not at all obvious. But if we go from integers to rational numbers, it turns out this has infinitely many solutions. But this is much deeper than this one, because to understand this, you have to bring out some more geometric structure for this cubic curve. This is what's called an elliptic curve. And by knowing about the number theoretic properties of elliptic curves, one can understand where these are coming from. But this is a much harder problem. There's no elementary formula for describing these on par with this one. And then when you go to higher degree, or more variables, things become somewhat more complicated. But if we focus, let's focus for a little while on this class of examples, because this turned out to be quite rich. To y squared into x cubed plus some constant. The constant might be -2 or 8 or something else. And Mordell, who initiated a lot of the early results in the arithmetic theory of elliptic curves, for some reason I don't know, was very enamored of this family of equations. And he proved, in this case, many results which were later proved more generally about elliptic curves. And in particular, he proved the following theorem. So if you fix your integer k, as I said, it might be -2 or 7 or what have you, then this equation has only finitely many integer solutions. But the proof he gave was sort of a proof by contradiction, and so it gave no a priori bound on a box which would contain any possible hypothetical solutions. And so one could naturally wonder, how big can the solutions get? And it can be hard to guess. So for example, here, if you take k equals 24, so you can find a few small solutions, and then there's this little outlier. Okay? And it might make you wonder, maybe there's an even further outlier if you look bigger. But in fact, these turn out to be all of the solutions. But can you give an a priori bound? So let's first look at one more example. So here's another example of k equals 8. And here are the red dots. So this is the graph of the curve. And these red dots correspond to these points. These are all of the integer solutions. Well, except there's one more, which goes off the page. And then it turns out there are infinitely many rational solutions. So there's going to be a huge dichotomy between integer and rational points. But even at the level of the integer points, if you have a theorem that says there are only finitely many, sometimes there can be some that are much bigger than the others, and then it makes you wonder whether you've really found them all. Okay, so you need some theoretical argument to bound the box that would contain these possible integer solutions, or similarly in the rational case, bound the numerators and denominators so you know where to look, if you expect there to be only finitely many. But nonetheless, you could wonder, can you give an a priori bound in terms of this constant? So, yeah. That's actually in the exponent, okay? So I didn't say it was practical, but there's a bound, all right? So this can be, you can improve this a lot. So the ABC conjectures can be related to giving a much better bound. But anyway, but keep in mind e to the 10 to the 10. So later when we have certain unspecified constants, they can be pretty big. So Baker proved this effective bound, right? So effective, as I say, doesn't mean practical. It just means, is there some kind of formula in terms of the parameters that gives some upper bound? Okay, then you can try to do better. Okay, and then a few years later, Stark proved something better, which is this 10,000 can be brought to any number bigger than 1 at the cost of maybe increasing e to the 10 to the 10. I mean, again, maybe it's not so practical after all. Increasing e to the 10 to the 10 to some constant depending upon that exponent. Okay, so you have this kind of exponential bound on x in terms of this constant parameter k. All right, but you could wonder whether you could do better than this. Can we do better than exponential? Could you bound x by a polynomial in k? Again, maybe with some constants floating around that depend upon something. Okay? All right, and so there was a conjecture by a guy named Hall. This is not Marshall Hall, so it's, I think, some other guy, in 1971, that he conjectured, based on little more than numerical evidence, that for this Mordell equation, the bound on the solution should be at most some universal constant, like maybe 1,000, all right, times k squared. All right? It was known that you couldn't do better than this. And so if you wanted to believe that something like this might be true, then of course to get a guess on what this c might be, you just take various k's, find the biggest integer solutions you can find, and see what lower bound that gives you on the constant. And so if you take these values of k, and here are some known solutions, then it gives you a lower bound. If there's going to be some universal number that always works, then this will give us some lower bound on what it could be. And then no Melkes comes along and finds this monster relative to that. And then, okay, well, so 25 isn't good enough after all. Okay? So it's not really believed that this is true anymore, although nobody's ever given a theoretical argument that this couldn't be true for some constant, but now it's believed that you have to do a little bit worse on the exponent. Okay. And so this is the standard formulation nowadays, what's called Hall's conjecture. You give me a constant k, that all the integer solutions, you should have this bound. You fix your choice of exponent bigger than 2. And there's some constant, but it might be e to the 10 to the 10. But anyway, some constant which is fixed only in terms of your fixed exponent. Okay? And well, let's see if this goes any better. So let's try to get by with epsilon is 1/10. Okay? So could there be a constant that always works the 2.2? And here are the solutions. And the lower bounds are not increasing quite as badly. But again, these are just numerical examples. This doesn't prove anything. Okay? But this is commonly believed to be true nowadays. And we'll see this is a consequence of the ABC conjecture. And that will even produce this epsilon and this constant. Okay? But one thing you have to keep in mind, when we get to the formulation of the ABC conjecture, it's going to have some implicit constants that depend upon some epsilon. And so if you prove this conjecture without giving a mechanism of bounding the constants depending on epsilon, then you can't use the conjecture to explicitly bound solutions to Diophantine equations. So the ABC conjecture, once we formulate it, can immediately prove various finiteness theorems. But if you want to use the conjecture to actually give explicit bounds, then the conjecture has to be proved in an explicit form. And so we'll come at the end to the issue of whether Mochizuki's proof, if it's correct, actually gives such results. Okay, so let's now turn to another class of Diophantine equations. So we'll connect up Hall's conjecture to the ABC conjecture a bit later. So here are two very famous so-called exponential Diophantine equations. And so these are equations where the exponents involve some unknowns. Okay, so the most famous being Fermat's last theorem, which was, of course, solved in the mid-90s. And then there's Catalan's conjecture, which you might call, it's the theorem 9 minus 8 equals 1. You're looking for perfect powers, non-trivial exponents, that differ by 1. And the conjecture by Catalan, which of course means it's probably due to somebody else, is that this is the only example. Okay? And this was actually settled a little over 10 years ago by using algebraic number theory methods and a little bit of analytic number theory. But before this work was done, again, in the spirit of e to the 10 to the 10, it was known that, in fact, that if there were any solutions, that there were actually explicit bounds, but they were far too large to be checked on the computer. Okay? This played no role in the eventual solution. So Miulescu's argument was theoretical, and it gave explicit theoretical bounds that were so small, and then you could sort of check the rest. But it didn't involve anything, it didn't require any work on the computer for ridiculous bounds like that. Okay? And so what we want to do is, again, these look quite unrelated to each other, but we'll see even for these so-called exponential Diophantine equations, in fact, the ABC conjecture, once we formulate it, will give us results, will let us make progress on questions like this. So let's now turn to this. What is this conjecture? So I have to introduce one piece of terminology. So the radical of a positive integer, we factor into primes, and then you just forget the exponents. Okay? So you just take all the primes that show up, and you just drop the exponents. Okay? So the radical can be much smaller than the original number. Okay? And we'll see that in the case of exponential Diophantine equations, losing the exponent actually has striking consequences. One thing I want to point out, though, which is, of course, the definition of the radical involves the prime factorization. But there's Euclid's algorithm. If you want to compute the greatest common factor of two positive integers, you don't have to factor. Right? Euclid's algorithm, just using long division, you can compute the GCD without factoring. So it's not, in view of that, even though the definition of this might be expressed in terms of prime factorization, you can really compute it without getting the individual prime factors. And so you might wonder if there's a way to compute the radical without actually finding the prime factors. And I just want to stress that actually there's no known way of doing this, even theoretically. Okay? With polynomials, it's different. You can find the radical of a polynomial by computing the GCD against the derivative. But for numbers, there's no analog. So when we compute things with radicals, you really have to compute the prime factorization. Okay. So the ABC conjectures are going to concern a very subtle relationship between the adding numbers and computing radicals. So radicals are a fundamentally multiplicative operation, it has to do with the prime factors. And we're going to try to understand the relationship between a plus b and the nature of the prime factors of a, b, and a plus b. And in particular, what I want to consider in a couple of examples is the following question. Could it happen that a, b, and a plus b all have their prime factors showing up to huge exponents? So huge that when you take the radical and forget the exponents, it drops to being below a plus b. Okay, so can that ever happen? And the basic idea of the ABC conjecture is that this is a very difficult situation to arrange. So let's just, for example, numerically, if you take all co-prime integers between 1 and 100, there are only these cases are the only ones where a plus b is bigger than the radical. And again, the way you want to think about this is somehow a and b and their sum should all have, in some sense, prime factors showing up to pretty high exponents. Okay? Now, in fact, well, okay, let me not get into this, but there is a construction that you can do, which, given any, taking a equals 1 and b equals this thing just less than a power of 3, you can, in fact, make this ratio be arbitrarily large. But what you'll see, what is very difficult to arrange, is that if you raise the radical to a power anything bigger than 1, then it's very difficult to arrange. And so this is what I want to actually focus on. Okay? So I'm going to give you integers a, b, and c. C is just a plus b, just to save the notation. And we saw, so it can happen sometimes that a, b, and c all have prime factors, if they have any, to large exponents. But in fact, it's very difficult to, if you put a little exponent here, this will then generally be bigger than a plus b. Right? In fact, there is no known example where a, b, and c are such that when you take the radical, that it actually drops below the square root of c. When you square it, it's always bigger than c. And people have checked very large ranges. Right? There are only 3 known counterexamples to this, and only 13 counterexamples to this. So if we try to compare the prime factorization of a, b, and a plus b in the guise of the radical of the product, and see how that is compared to the sum itself, if you raise it to an exponent bigger than 1, it seems to be very hard to make this bigger than the sum. Okay? And that's the ABC conjecture. All right? You give me any exponent bigger than 1, and if you give me any a and b that are co-prime, and c is a plus b, that if you take the radical to that power, that this will always be bigger than the sum with only finitely many exceptions. Now, I want to stress 2 things. If we're going to apply this to various Diaphanetin problems, you need, in an explicit form, you need to be able to bound where these finitely many exceptions can occur. And this is going to be related to this, some of those things I said before. Okay? And the other thing I want to stress is this is a kind of all or nothing conjecture. It's very important to, you want to be able to get this for small epsilon, as we'll see, but in fact, there is no known example for any epsilon, no matter how small, where this has been proved. Okay? This is a very, very subtle problem relating, as I said, the prime factors of a, b, and a plus b in some kind of very subtle form. Okay? And here...
you said this has been proved. What was the if?
No. So nothing has been proved, not even for there's been no epsilon for which this statement was proved. For many applications, you want to know this for very small epsilon. Okay? Like even proving, for example, proving this would be an amazing achievement. But for many applications, you need the exponent to be much less than 2. So it's important, you want to get this for epsilon arbitrarily small, but there is no epsilon for which this was proved. So in that sense, you could have partial progress, but even that is sort of considered to be sort of beyond the reach of possibility, aside from Mochizuki's announcement, which we'll come to at the end. So here are some examples where you have, for example, sum of 3 numbers. All right, and see here you have some large exponents, right, 4 and 6, and here these are all showing up to small powers. Okay, and here you have large exponents, and the primes show up to small powers. And so again, the basic thrust is it's very hard to get it where all the primes are showing up to high enough multiplicities so that when you took the radical, somehow it could drop to be below the sum. Okay? Now, I should say there are examples. So here's an example where you do have a sum of 2 numbers, and so that the individual numbers in the sum all have non-trivial exponents for the prime factors. But even here, in fact, the comparison to the radical is just a little bit more than 1. Okay? So this is the basic tension between relating the multiplicity of prime factors of the sum with the multiplicity of the prime factors of the individual numbers. And that's somehow the subtlety, and it's very difficult to relate these kinds of additive and multiplicative problems. Okay. I want to give 2 other reformulations because they'll connect back to the examples of Hall's conjecture and Fermat and Catalan. So there's a kind of trivial reformulation that you might allow the numbers to be negative, okay, and then you just throw in some absolute values. That's not so interesting. In fact, to make the problem more symmetric, sometimes we bring c to the other side. You say a plus b plus c equals 0, and then you just make a symmetric statement about the absolute values. Okay, but this is just a trivial reformulation of the original problem. And if you want to allow for the finitely many exceptions, if I fix epsilon equals, let's say, 1/5, and there are a finite number of counterexamples to this, where this side is bigger, then you just stick a factor of 10 gazillion here, and then you'll make the side bigger to counteract the finitely many counterexamples. So instead of talking about finitely many counterexamples to this version, you just allow yourself to put some unknown constant in here depending on epsilon, and then you can make a universal statement. And so often one sees this formulation, and this is going to really connect back to things like Hall's conjecture, that for a given exponent, you have some inequality with some constant that you don't know. All right? And if we want to prove the result in a form that we can actually apply it to give explicit bounds, we're going to have to know what this constant is. And so we'll come back to that a little bit later. Okay? And in fact, in the original announcement by Masser of the conjecture, this is the version in which he formulated it, that you have 3 numbers a, b, c that are co-prime who sum up to 0, because he brought c to the other side. And then he phrased it this way with some constant, and then this is just the radical raised to that power. Okay. So why did they think about this conjecture? So this is in principle, Gauss could have thought of this conjecture, right? There's nothing, very advanced in the statement. But in fact, the reason that they were led to it, was only they only came up with in the mid 1980s, and the reason was the following. So Sphero was studying the arithmetic of elliptic curves. So these are special kinds of cubic curves, such as this one, which we graphed earlier. And Sphero made a conjecture about certain arithmetic properties of these guys. And Oesterlé was trying to think about other ways of formulating Sphero's conjecture. And then when Masser heard Oesterlé give a lecture about it, he decided to see if he could reformulate Sphero's conjecture in a form that didn't even mention elliptic curves at all, and that led him to this. So there is a conjecture within the framework of elliptic curves, which I'm not going to formulate here, which turns out to be actually equivalent to this. And suffice to say, it gives you a lot more structure on the problem. And Mochizuki's work really took place entirely in the world of elliptic curves and related constructions in algebraic geometry. But this formulation is very well suited to applications to Diaphanetin equations. So this is what we'll mainly talk about. And in fact, later it was realized that the ABC conjecture has consequences such as Fermat's last theorem, but this historically had absolutely no role in the original formulation of the problem. Okay, that kind of came as a surprise later. But they did realize pretty quickly that it did have quite spectacular consequences to Diaphanetin equations, and so I'm going to explain these to you.
Does the application go through elliptic curves?
For which one?
ABC implies Fermat.
ABC implies Fermat does not. In fact, I'm going to show you this. This is completely elementary. Now, I should say, ABC implies Fermat for large exponents. And how large the exponent depends on the constants. Okay, but this one I'll show you in about a minute. So that doesn't go through elliptic curves. Okay, and so as I was saying, there are different ways of applying this kind of statement. If you want to just use this to prove finiteness theorem, certain kind of system of equations has only finitely many solutions, and you don't care about bounding them, this version is often sufficient. But if you want to give explicit bounds, then you have to control the finitely many, all right? And it may be that the epsilon has to be very small. Okay, so we'll see this in a couple of examples, that to apply this to certain kinds of Diaphanetin equations, you need epsilon to be maybe like less than 1/5 or less than 1/2. Okay? Okay, and as I said, prior to Mochizuki's announcement of the general case, nobody had ever announced a proof of this for any epsilon at all. Okay, so let me first, to answer Dennis's question, let me first show why this implies what we might call asymptotic Fermat. All right. So let's suppose you had a hypothetical counterexample where the exponent was at least 3. And what we're going to do is, well, first we're going to bound the exponent, and then we're going to also get bounds on, in fact, the x to the n, y to the n, and z to the n as well. Okay, and so it's actually, well, you could say it looks very elementary. Of course, I'm going to be using the ABC conjecture. Okay, so of course that's the hard part. All right, well, let's see. A plus B equals C. And because the equation is homogeneous in x, y, and z, you can scale it down so x and y don't have a common factor because the exponents match up. So you can get this to the case where these 3 numbers are co-prime. And so it's an example of an ABC triple. And so A plus B is C, and this is the biggest. And so therefore, if the ABC conjecture is true, with finitely many exceptions, this triple should satisfy this inequality for some epsilon. You maybe pick epsilon equals a fifth, or a half, or 2, or whatever. Okay, well, oh, radical, great. Goodbye exponents, okay? And then x and y are at most z, right? And so that gives you most z cubed. And so therefore, and the z is, of course, at least 2. And so anyway, n is bounded by 3 to 1 plus epsilon. Okay, so if you could prove, this is a big if, of course, right? So if you could prove the ABC conjecture for some epsilon over all ABC, then you would get an explicit bound on n. Moreover, even if even if n, if you had any counterexample, right? You had the counterexamples, then you'd have these small numbers, all right? And the point is that so once you get a bound on n, all right, then you can of course try to refine the argument and get bounds on x, y, and z. But the thing I want to stress is this will not tell you. So if n is bigger than this, then you're in this exceptional case. So if you actually had ABC for a given epsilon with the known exceptions, then you could use this to rule out Fermat for exponents above this bound. This tells you nothing about exponents below that bound. Okay? So this argument would never actually settle Fermat's last theorem unless, of course, you had it for some really, really small epsilon. Okay? But anyway, of course, you could say this is moot because we've already solved Fermat's last theorem. And suffice to say, Weil's proof of Fermat is much more elementary than what Mochizuki did, if what Mochizuki did is correct. So I'm not claiming this would even give you a simpler proof. But this is quite typical of these applications. But we're going to turn to the Catalan conjecture next. Okay? So it implies asymptotic Fermat. But note again, how good a bound you get on n depends on how small you can make epsilon such that you could actually prove this conjecture. Okay. And let me just point out, I mean, this is a kind of silly variant. You could do little variations, like put a constant in there, 5, let's say, right? And again, you can play the same game, A, B, and C, with some finite set of exceptions. You do the same trick where you get rid of the exponents, and then it turns out that if m is the largest, you get an explicit bound on m to the n, and eventually you get a bound on n in terms of this epsilon, okay? But then it involves the number 5. Right? In any event, so given these kinds of homogeneous exponential Diaphanetin equations, ABC of this very special sort, then you can use ABC to qualitatively understand where the exceptions might be located if you had epsilon small enough. All right? And for this application, right, you need epsilon to be less than a third. Okay? Let's now turn to this kind of higher exponent version of Pell's equation. Does anybody have any questions about? But I just want to stress, it's useless for an application to a specific class of equations unless you knew where those finitely many exceptions were. Okay, it's not going to say, oh yeah, Fermat's last theorem is true except for some unknown finite set. Not quite. Okay, so now let's look at this this cubic version of Pell's equation. And let's see that if you use so this turns out to have only 2 integer solutions. That's not at all elementary to prove. But let's see that if you knew the ABC conjecture, for epsilon less than a half, then it would tell us there are only finitely many. And once again, if this came with an explicit bound on the exceptions, you could then hope to use it to give you the 2 explicit ones and no others. So let's see how it goes. All right? Well, here's A. Of course, obviously, x and y have no non-trivial common factor. Here's A is x cubed, B is negative 7y cubed, and C is 1. All right? So with a finite set of exceptions, right, A and B, right, they're bounded by the maximum, the sum, I'm sorry, excuse me. All three in absolute value are bounded by the maximum. I'm going back to this, sorry, let me just go back. Using the symmetric formulation of the problem. The other formulation involved positive integers, but when we allow negatives, then we have all three are bounded by the radical, okay, to that exponent. Well, once again, we lose the exponents, all right? And look, you see you have exponents of 3 on this side and 1 plus epsilon on that side, and so that's good news, okay? And so if you take the maximum, which is bounded, and of course the maximum is bounded in terms of the product, all right? And then if you just plug it in, you get the maximum is bounded by this expression. And so as long as this expression here is less than 1, then you're in very good shape. Okay? So as long as epsilon is less than a half, then in fact you get an explicit bound on the maximum in terms of epsilon. But I want to stress, I've only proved this bound on the maximum away from the finitely many exceptions that are part of the statement of the ABC conjecture. Okay? So if you knew the ABC conjecture for some explicit epsilon, then this would tell you that, yeah, all the integer solutions are in a box bounded by this explicit number with a finite exceptional set. Okay? So if you had explicit control of this, then you could use this statement to actually give a direct proof of this, and hopefully for other Diaphanetin equations of that flavor. And similarly, if you take the exponent, instead of being 3, if you take it to be some bigger integer, then you need ABC to be at most n over 2. Minus 1. So the thing I just want you to take away from this is ABC is well suited for giving bounds on certain special kinds of Diaphanetin equations, but you have to have epsilon small enough, and if you want to use it to give explicit formulas without exceptions, then you have to have control on the exceptional set in the statement of the conjecture. Now let's look at Catalan. Okay? So here's the version, the very first weak version of ABC that I formulated with a full exponent was 2. There is no known counterexample to this. So this is the case epsilon equals 1. So let me show you that if this were actually true, then that would imply Catalan's conjecture that 9 and 8 are the only perfect powers that differ by 1. But the advantage, I should say, Mihalescu's proof of Catalan's conjecture, it's very important that the number 1 is there. So you might wonder about perfect powers that differ by 3. Or 12, or some other fixed constant. Mihalescu's proof doesn't help with that. But the method using the ABC conjecture can analyze all of those. Okay, so it's a much more robust way to analyze those kinds of questions. So, well, let's see. So here we take our A, B, and C, these 3 numbers. The GCD is 1. And so the biggest of them is bounded by the radical. You drop the exponents from the radical. And so you can see that if n is bigger than 2, this is already not looking so good. Okay? And then if you just do a little bit of algebra, eventually what you find is that you do actually get, as long as you assume that x and y, that the exponents were actually at least 2, then if you fiddle around with the algebra, you eventually do get this bound. All right? And so you find the only possibilities for n and m, well, one of them might be 2, and the other one you can't control. Or they could be one of these 3 pairs. But it turns out that in the 60s, the analytic number theorists, or people had actually analyzed this class of examples of exponents and had shown that there were no such examples. Okay? And so, of course, the only reason we can make progress on this is you could turn the bound of the numbers into a bound of the exponents because, of course, the y is bigger than 1. All right? So on the one hand, in this case, if you had this special case with epsilon equal 1, then you get bounds on the exponents to some finite set, and then those have to be analyzed directly. And I should stress that, and as we'll see a little bit later, that actually even if you replace 1 with another constant, the ABC conjecture is well suited to actually giving bounds in that case. But again, you need to have some specific exponent that's adapted to the particular constant that you choose.
Those sets of pairs of integers?
Yeah.
If you look at spherical triangle groups that contain at least 1, 2, it's the same set.
Yeah, this is just an accident to the algebra. There's certainly there's no direct connection. Yeah. This is just a quirk that we wound up getting this expression 1 over m plus 1 over n. So, I should clarify that it is certainly the case that people have looked at things like what you might call kind of generalized Fermat. A to the p plus b to the q equals c to the r. right? And in that case, actually, what you expect for the behavior of the integer solutions is in fact controlled by things like 1 over p plus 1 over q being related to 1 over r. But in this case, it's just a kind of quirky element. Okay. All right, now let's come back to something I discussed before, Hall's conjecture. Okay? So that was the conjecture that in this Mordell equation, all the solutions, the integer solution, should be in a box. The x should be bound by some, remember, this constant might be e to the 10 to the 10, so don't get your hopes up. Some constant k to the power bigger than 2. All right? And in fact, I won't go through the argument here, but the ABC conjecture actually implies this. In fact, it implies a stronger form. You even have a bound with the radical, whatever. But here's the amazing thing. The radical implies the ABC conjecture. So in other words, this Hall conjecture about this class of equations, in fact, turns out to imply, but of course this is not at all easy, but in fact you can actually use this by using, you have to use things with elliptic curves, you can actually use the radical Hall conjecture to actually deduce the ABC conjecture. Okay? And as I said, the ABC conjecture has many other consequences that are unrelated to Diophantine equations, so it's quite striking. But this also basically should make you realize that this is actually a much more difficult equation to understand than you might have thought. Meaning bounding explicitly the integer solutions is a fundamentally hard problem because it's actually equivalent to the ABC conjecture.
So Mordell knew what he was doing.
Sorry? Yeah, he actually had very good taste, it turns out. But notice he didn't get the explicit bounds. Right, but he hit upon a rather rich, rather difficult class of equations. Okay, and as I was saying, for the Catalan, if we replace 1 with another number, then in fact this you can also analyze, and it's in fact generally believed that yes, for any given constant, so the perfect powers, especially if you have co-prime exponents, it's very hard to see whether you have any two that are close to each other. Obviously, consecutive cubes keep growing and growing, but if you want to compare cubes to fifth powers, it's not obvious. Maybe if you go far enough, there's a cube very close to a fifth power. It's very hard to tell. Okay? But in fact, if you knew ABC for some epsilon less than 1/5, then in fact it would follow that for any constant k bigger than or equal to 1, that this has only finitely many solutions. There are only finitely many perfect powers that differ by 7, that differ by 8, that differ by 10, and so on. But you have to know ABC for epsilon small enough. But notice this is good enough for all k. Well, if you knew the ABC conjecture, but no. Okay, let me do one last application, which is actually quite spectacular. It's called Ross' theorem. So the very classical problem, what's called rational approximation to irrationals. So if you take an irrational number, of course it has its decimal expansion, and then you might ask, how close can you get a rational to that number? With the error, you want to be pretty good in terms of the denominator. So obviously, you can get something whose error is on the order of 1 over b. All right? But you could ask, can you get something where the error is on the order of maybe quadratic in the denominator? So it's an unusually good approximation relative to the size of the denominator you were giving yourself. All right? So for example, if we just do the naive decimal approximation to 3 digits, this is basically only good to within 1 in 1,000 because the error is already there, right? 6 over 10,000, whatever. But in fact, there are fractions which give you even quadratic level of approximation, and these are made using what's called the theory of continued fractions. Okay? So there's an infinite, for any irrational, fifth root of 2 or whatever, there's an infinite sequence of rational numbers which give you unusually good rational approximations to within quadratic error based on the denominator that you were giving yourself. For example, of course, the most famous example is known as pi. Right? 22/7 has 1 digit, but it's good to 2 decimal digits, right? Or the next one, right? 355 over 113, right? And that's good to 6 decimal digits. So for every irrational number, there is an infinite sequence of rationals that give you an approximation to within quadratic error based on the denominator. And then you could ask, can you do better? Okay? So if we take those good rational approximations, and you see, well, okay, they're within 1 over b squared, but how good are they within 1 over b squared? And so if you take these guys and you plot them, you see that as you go further and further out, they all start falling below any line you choose. So you cannot find, or it does not seem that you can find within that sequence, a subsequence which is good to within some exponent even bigger than 2. And in fact, it's a theorem that there are only, for any given horizontal line, for any given tolerance epsilon, you will not be able to do better than 1 over beta to the 2 plus epsilon for an infinite sequence of rationals. There are only finitely many that do that well. Okay? And in fact, Roth proved this in general. For any algebraic irrational number, if you try to get within 1 over beta to the 2 plus epsilon on the approximation, there are only finitely many examples. Okay? And he actually won the Fields Medal for proving this. Okay? So this is a very hard theorem. But, you might say, where are the exceptions? How far do you have to search to find for a given epsilon? How far do you have to search? And Roth's proof was, again, a proof by contradiction. It was completely ineffective. Well, it turns out that you can actually use the ABC conjecture to analyze this. And so to see the connection, this was the formulation, the ABC conjecture I gave before. But of course, you could bring the exponent to the other side, bigger than 1 to less than 1. So this is another formulation, a formulation in terms of lower bounds. Okay? Given an ABC triple, the radical can't be too small, can't be smaller than a given fractional exponent of the maximum. Okay? And in fact, it was proved by Elkies and Langevin that actually the ABC conjecture can be used to prove Roth's theorem. All right? More explicitly, you can deduce the entire theorem of Roth from the ABC conjecture, and if you had an effective version of ABC, meaning for a given epsilon, you could bound where the counterexamples were located. In fact, you could deduce Roth's theorem in an effective form. And to this day, there is no effective known version of Roth's theorem. Okay, so this would be an amazing achievement. Of course, if you knew the ABC conjecture, that would already be spectacular enough. Okay? So let me just end. I just want to say, in terms of the slides, I just want to say a couple of things about what Mochizuki did. So first you might say, well, you're not giving yourself very much. Like, what structure are you using? A plus B is C. Just fiddling around. Like, when we made this deduction of Fermat's last theorem, you sort of feel like you're getting something for nothing, but of course, you're granting the ABC conjecture. So obviously there's some meat in there. So like, what do you do with this? Okay? And then the separate issue is, if you dig into his proof, if it's correct, if you dig into his proof, does it give you explicit bounds? Okay. And so the first thing, and this is actually exactly what came up in the case of Fermat's last theorem. So when Weil solved Fermat's last theorem, the traditional approach to Fermat's last theorem using algebraic number theory, right, that went through the theory of cyclotomic fields. You took the explicit Fermat equation and you factored it and you actually did arithmetic working with that equation. And then the approach that Weil's used, going back to Helgeruch and Frey, was you had this initial equation, you associate a geometric object, this equation, this elliptic curve, and then you bring in the full force of the arithmetic theory of elliptic curves and all kinds of mathematical structures that are related to elliptic curves that give you something to work with. Of course, you have to interpret something about the properties of the numbers a, b, and c in terms of the geometry or the mod p reduction, or something about the interesting arithmetic properties of this curve encoding whatever it is that you cared about with these guys, like the radical or whatever. Okay? And in fact, Mochizuki was the same thing, where instead of thinking about this equation, he actually thought about the so-called Sphero conjecture, which I have not stated. Of course, those of you who care can just go to Google and type Sphero's conjecture. And so Sphero's conjecture is a statement about not just these elliptic curves, but all elliptic curves. And in that formulation, of course, it's a much more robust framework. You could do operations on the elliptic curve, pass to isogeny classes, and think about moduli spaces and other kinds of constructions, which you can't do with these individual guys. And so in fact, Mochizuki is not aiming to prove the Sphero conjecture for these elliptic curves. He's going to think about all elliptic curves and their moduli spaces and do a lot of work in algebraic geometry and eventually deduce the result. But in fact, the nature of his method does not lend itself to understanding the exceptional examples. And the problem is, so in order to prove this theorem, of course, you have to catch all A, B, and C. All right? So you have to catch all these Frey curves or all these elliptic curves. And in Mochizuki's arguments, he had certain arguments that only applied to elliptic curves whose Galois representations, whose associated arithmetic structures exhibited certain kind of generic behavior. And then, of course, those are not all of them. And so if you need to catch everything, you need some special arguments to deal with the non-generic cases. And in those situations, he had to apply a technique that goes back to a mathematician called Bellier. And this involves certain very indirect arguments that are very hard to make explicit in a kind of abstract setting. In any specific case, you can make these explicit. But in a theoretical way, if you want to get theoretical upper bounds on exceptions, you have to deal with this step. And this step involves some very complicated iterative algebraic procedure. And so it's very hard to get explicit bounds out of that. And I should say that, like, back in around 2000, I was visiting Japan. And I was at RIMS, and I dropped by Mochizuki's office. And so I asked him at that time, I said, oh, do you think that the methods that you're using to think about this look kind of abstract? Do you think that you'll eventually be able to get explicit constants out of it? And he looked at me, and he said, what do you mean, what explicit constants? So in any event, so on the one hand, it's really not clear that, assuming that his results pan out, that in fact it will be in a form, at least at the initial stage, that's well suited to giving explicit bounds. So it will be very good for proving abstract finiteness theorems, but if one wants, of course, to apply this to say, this equation has only these 5 solutions and so on, then one will have to understand the proof in a better way in order to get those kinds of explicit bounds out. Well, that was actually the last slide anyway. So, okay, thank you.